So the strength of acids depends on a variety of factors. Let's take a look at the factors influencing. So what do all strong acids have in common? Yeah, they dissociate completely. The easier they dissociate, the better. This is showing gas phase dissociation. And so the easier it is to break off the H plus, the better. And how easy is it to break off the H plus depends on the bond energy. And so acid strength can depend on one, the bond energy, or the bond dissociation energy, or just the dissociation energy. The easier it is to break, that is, the weaker the bond, the stronger the acid. And therefore, things like weak acids partially ionize, dissociate. Strong acids fully ionize, dissociate. The next factor that we look at is bond polarity. The more polar the bond, the higher the positive charge on that bond. And the higher the positive charge, the more attracted the base will be. The base is going to be attracted to H plus. Usually, H plus is acid. So this base will be attracted to that. 3, the stability of the product. The product in this case is going to be the conjugate base or just the base. There are other factors that could influence things as well. Other factors, this is just for HF. We have something called ion pairing. Ion pairing. All right, so let's look at bond energy first. There are 2 ways to break the bond. They're shown here. The typical bond energies that we look at in the table are this style of breakage. This style of breakage is called homolytic bond cleavage, bond break. This style down here is heterolytic. So if we have an HX bond, we can break it homolytically, which means we break it in half. One electron goes to the hydrogen, the other electron goes to the X. Or we can break it heterolytically. That is, we break it so that both electrons go to X. And so it leaves H positive and X negative. The dissociation energies that we find in the tables are homolytic. But for acids, we want to do heterolytic. And so so we don't have those numbers in the table. We just have the homolytic numbers. The homolytic numbers is DHX here. But we don't have the DH plus X minus, the heterolytic. But we can figure it out using Hess's law. I mean, we could measure it, but it's easier to just use Hess's law to determine it. And so if we do it in multiple steps versus doing it in one step, we'll get the same answer. The sum of the steps is equal to the net overall. And so if we do a homolytic cleavage here, we'll get H. And then we need to take an electron off H to make H plus. Well, to take an electron off H is the ionization energy. And so that's E sub I there. EI1 for hydrogen. And so we'll have H plus. So now what we have to do is we have to add the dissociation energy, the homolytic, and then add the energy cost of stripping an electron off hydrogen. But we also need to go and form X minus here. We form X minus, that's electron affinity. So this is enthalpy for the electron affinity, which is adding an electron. And so we have to add that. And so the sum of the steps, step 1, step 2, step 3, we'll just add these three, should give us the net overall. And so we can figure out that overall. So the homolytic dissociation energy is shown here in this row. So the hydrogen-carbon bonds 414, hydrogen-nitrogen 389, hydrogen-oxygen 464, and hydrogen-fluorine 565. So based on the homolytic, which one's the strongest bond? Yeah, this is the strongest bond. Break this. And what we said is the stronger the bond, the weaker the acid. The weaker the bond, the stronger the acid. So as far as bond energy goes, we want weak bond equals strong acid. Strong bond, weak acid. So the strongest bond's here, HF, so that should be the weakest acid. But the weakest bond, HNH2, to the ammonia, should be the strongest acid. But is that the case? Is ammonia stronger acid than hydrofluoric acid? No. Ammonia is usually thought of as base. This is wrong. It's wrong because we're looking at the homolytic energies. We have to look at the heterolytic energies, and that's going to change things a bit because fluorine has a very high electron affinity. Wants electron. So when you look at the heterolytic bond energies, then which one is the weakest? HF, and therefore HF should be the strongest acid, and it is. And so here's a correlation with bond energy. Bond energy tells us HF should be the strongest acid. The next thing we look at is bond polarity. Bond polarity tells us, well, which one of these bonds is the most polar, has the greatest delta EM, difference in electronegativity, HF. So bond polarity tells us HF should be the strongest acid, and it is. How about stability of the products? Stability of the products means how well can the conjugate base be stabilized in water and other things. So we'll look at stability of the product in the next example here. Let's compare HF versus HCl. In terms of bond energy, which one should be a stronger acid? HCl. HCl's got a weaker bond, therefore it should be a stronger acid. And that's the case, HCl. In terms of polarity, which one is more polar, HF or HCl? HF is more polar. And so what we have is we have conflicting factors. On the one hand, bond energy tells us HCl is going to be stronger. On the other hand, bond polarity tells us HF is going to be stronger. And so how do you weigh those? You know, which more important, the bond energy or the bond polarity? How we weigh those is we look at the data, the experimental data. So this is the two-pronged approach. We're going to use some theoretical with experimental. And here we see, well, you know, which one's a stronger acid? HCl. And the thing we can measure as far as strength goes is this constant called Ka, case of A. That's this top number here. The bigger the Ka, the more dissociation we have. The smaller the Ka, the less dissociation we have. And so Ka gives us an idea of how much dissociation, more dissociates, the stronger the acid. And therefore, we see that HCl is much stronger. In fact, orders of magnitude stronger. If we look at it, it's 10 orders of magnitude stronger. 10 orders of magnitude would be 10 billion. And so essentially, HCl is 10 billion times stronger than HF based on the Ka values here. But the situation is this. If HF is 10 billion times weaker, then does that mean HF has a bond that's 10 billion times stronger? Yeah, it makes sense. If this is 10 billion times weaker, it must have a 10 billion times stronger bond. But when we look at the bond energies, the heterolytic, we'll ignore the homolytic here, and look at the heterolytic, it's 1549. Yes, it's stronger versus 1394, but 10 billion times stronger? No. And so that means there must be other factors at play. So what are the other factors? The other factors would be stability of the product. And so let's take a look at the product here for HF versus HCl. So we'll just, we can either put these in water or, actually these are going to be in water. Those Kas are for aqueous. And so when HF reacts with water, or hydrolyzes water, it's going to form hydronium and fluoride. This is a weak acid, so it's a two-way street. Whereas when HCl hydrolyzes water, it hydrolyzes completely, essentially, close to complete. Well, that's because we know one's a strong acid, the other's a weak acid, but how about the products? Well, hydronium is the same in both. So the products are fluoride versus chloride. Which is more stable in water? Fluoride versus chloride. So one big difference is fluoride. Fluoride has what shells filled? It's got the first shell and the second shell filled. So it'd be isoelectronic with neon. Neon's pretty small, so fluoride's going to be kind of small as well. Not as small because it doesn't have as many protons as neon, but small. Chloride fills up through the third shell, so chloride's going to be bigger. So when we look at stability of the products, we look at two things. We look at how concentrated the negative charge is. The more concentrated the negative charge, the stronger the base. Actually, it looks like a base strength. Since these are bases, these are conjugate bases, and with a base strength. One is the magnitude of charge. So if one is -2, the other is -1, the -2 is going to be more basic. -2 will have an easier time plucking protons off than -1. These are the same though, both are -1. 2, we look at the concentration of charge. And so we call that like charge localization, delocalization. We have different factors influencing this. We have something called inductive effect. In which the charge might be pulled by another atom bonded to it. Here, there's no inductive effect. 2, we have resonance delocalization. Okay, in this case, the charge is what we say localized. And so the charge is localized on this fluorine. There's only one atom, so that fluorine is going to have a negative charge, and the same thing here. There's no delocalization in this. Okay? So if there's no delocalization, and the charge is the same. If we look, the charge is the same here, but is it really the same? In one sense, the overall total charge is the same, but in another sense, the charge on fluorine is more concentrated than the charge on chlorine. And so this is going to have a higher charge density than this. The higher the charge, or charge density, the stronger the base. So these two, which one's stronger? Fluoride. Yeah. Fluoride is stronger. Is a stronger base more stable or less stable? Less stable. So based on charge density, fluoride should be less stable. So when we look at the stability of the conjugate base, we're looking for weaker base. Weaker base is more stable. And we're looking at size. The size because of something called hydration or solvation. These ions are stabilized by having water molecules surround them. And when water molecules surround them, the positive end of the water molecule is oriented around the negative anion. This is called an ion dipole attraction. This is a dipole of water. And so we probably can fit about 6 water molecules here. 4 kind of in the plane, 1 on top, 1 on the bottom. We call it a hydration sphere or solvated ion. Then we think about Coulomb's law. Which one's going to have a stronger ion dipole attraction? Fluoride or chloride? Fluoride. There are 2 ways of thinking about it. One way is that fluoride is more concentrated negative charge. The second way is in terms of Coulomb's law. Coulomb's law says the force of attraction is going to depend on the charge, ZA, the charge on A and B, ZB, divided by the distance between the center of the charges squared. And so here's where the size effect comes in. Here there's going to be a shorter distance. Here there's going to be a longer distance between the centers of the charge. And so this is going to be a much weaker hydration sphere. This is going to be a much stronger hydration sphere. So in terms of solvation, fluoride's more stable. But in terms of base strength, fluoride is less stable, more reactive. So we have conflicting factors there. Since we have conflicting factors, we just look at the data and then we do an ad hoc explanation. That is, we aren't predicting it. We're just seeing what it is. And what it is HF is a weaker acid. But it's an unusually weak acid. And so let's talk about HF and ion pairing. Because of the small size of fluoride, it's very reactive in a Coulombic fashion. And so if we have HF and water, this is going to form hydronium and fluoride. The fluorides are going to be well solvated by water, but what's better than water is hydronium. But it's not quite good enough. And so what happens here is this, good enough to completely reverse it. What happens here is that the fluoride does not completely dissociate from the hydronium. In other words, the fluoride is still kind of stuck onto the hydronium. It's not bonded, but it's got a strong ion-ion attraction. This strong ion-ion attraction is called an ion pair, and it requires additional collision to break the fluoride free. We don't have to worry too much about ion pairs with chloride because of its bigger size. It's not going to be as significant. Since there's significant ion pair formation with HF, this is what makes it unusually weak. This is an unusually weak acid. Let's look at HCl, HBr, and HI. Based on bond energy, which one should be the strongest? So we're looking at the bottom one, which is heterolytic. Although the homolytic, we can look at the homolytic, it's pretty much the same. The strongest bond will be HCl, the weakest bond will be HI. Therefore, based on bond energies, which acid should be predicted to be the strongest? HI. Based on polarity, which bond is the most polar? HCl. So based on bond polarity, the strongest acid should be HCl. Based on base strength, which of these bases will be the strongest? Chloride, bromide, or iodide? Which one? Chloride's the strongest. It has the most concentrated negative charge. So based on base strength, this is the strongest, so therefore it's going to be the least stable. This should be the strongest acid. It's going to produce the weakest base. Based on solvation, i.e. hydration, which one will be the most stable? Hydrated chloride ions or hydrated iodide ions? Iodide or chloride? Well, what's the difference? Iodide is quite big. Chloride is a lot smaller. So which one is going to have a more stable hydration sphere? Iodide?
For Coulomb's law, like the F, do you want a large F stability or a small?
Small. The smaller it is, the more stable the hydration sphere is. The more reactive the base is. So we take these one at a time because they're conflicting. And so this is more stable than this. It's harder. If you wanted to pull the water away, which one would be harder to pull the water away from? The smaller one, because the negative charge density is more it's more concentrated here. The charge density is. So if the charge density is more concentrated here, it's going to be harder to remove the water, even though the total charge is the same. Does that make sense? So let me ask you again, which one is more stable, solvated chloride ions or solvated iodide ions? Solvated chloride, so that means HCl should be stronger. So we have these multiple factors that we look at, but the situation is, how do you weigh them? And so this is where the two-pronged approach comes in, because we don't know how to weigh them easily. And so what we're going to do is we're just going to look at the data. Which is the strongest acid? So we look at the Ka value. 10 to the 9th versus 10 to the 8th. Hi is 10 times stronger than HBr. And Hi is 1,000 times stronger than HCl. So what that means is the most important factor is for these three, the most important factor is polarity. If we pick polarity, we'd have the wrong answer. Is the most important factor hydrated ions? If we picked hydrated ions, HCl would be the strongest. Is the most important factor base strength? Well, chloride should be the stronger base. Could be. Bromide should be the weaker base. Weaker base is more stable, so it leads to a more stable product. But all of those bases are bad. Chloride, bromide, and iodide are so bad we call them neutral. And therefore, the most important factor is bond energy. And so typically we'll just say bond energy is the most important factor. And if that's not the case, then we start looking for other things. Take a look at these. H2S is hydrogen sulfide or hydrosulfuric acid. H2SE is hydrogen selenide or hydroselenic acid. And H2TE is hydrogen telluride or hydrotelluric acid. Okay, what do you predict? Which one should be the strongest and why? H2TE because it has the biggest bond energy, that is the strongest bond. Yeah. Would you guys agree? Where did you get the bond energy? Which bond energy are you looking at? Are you looking at the middle one, which is the homolytic bond energy? You look at the middle one, which one's the strongest and which one's the weakest? H2S is the strongest at 368. If you look at the heterolytic bond energy, which we should be looking at, we can ignore the homolytic and look at the heterolytic. If we look at the heterolytic, which one is the strongest? H2S. The stronger the bond, the stronger the acid, or the stronger bond, the weaker the acid? What is it?
Stronger bond.
Stronger bond, weaker acid, weaker bond. And therefore, H2TE has the weakest bond and should be the strongest acid. Which one's the most polar? Well, electronegativity goes up. And so H2S is going to be more polar than H2TE. So if we pick polarity, we get the wrong answer. As far as base strength goes, we might get the right answer. The base strength we're looking at is hydrogen telluride, HTE minus, versus hydrogen sulfide. Which one has the more concentrated negative charge? Hydrogen telluride or hydrogen sulfide? Yeah. Hydrogen sulfide because of the charge density, yeah. Sulfur is much smaller. Sulfur is third period and telluride is fifth period. got the negative charge on sulfur here. This tellurium here. This is the hydrogen over here. And so we can look at the charge density. The negative charge is more concentrated on sulfur than it is on tellurium. So if we picked the base strength, then we would have gotten the right answer. But we probably think the major factor here is bond energy. HF is a little bit unusual case. It's unusually weak because of formation of these ion pair. Ion pair means the hydronium isn't free. 3F. It's got a fluoride stuck onto it. You analyze these two acids. You recognize the first acid? Can you name that one? This one's hypochlorous acid versus hypobromous acid. Which one do you expect to be stronger and why? Oxygen. Sure aren't going to factor in. Bond polarities, if you look at delta En, it's the same. It's a hydrogen-oxygen. Hydrogen is 2.1, oxygen is 3.5. But there's going to be a secondary effect. So let's talk about that. It's called the inductive effect. Inductive effect is the Pauline's electronegativities aren't detailed enough. They're a little bit too broad and overgeneralized because oxygen's electronegativity changes depending on what's bonded to it. So if we were to compare the HO bond versus the HO bond, they're going to have the same polarity. However, the oxygen over here is in a tug of war with the hydrogen. And against hydrogen, oxygen wins. Oxygen is also in a tug of war with chlorine, and against chlorine, oxygen also wins. Over here, it's the same thing. Hydrogen versus oxygen wins. Oxygen versus bromine, oxygen wins. But then we have to factor in, if this is a tug of war, then chlorine, yes, oxygen's more electronegative than chlorine, but chlorine is more electronegative than bromine. So this is a 3.0, that's a 2.8. And so in the struggle on this bond over here, we're going to see this. Chlorine is going to be able to hold on to more of the electron cloud than bromine. Bromine is a bit weaker. Since it's a bit weaker, it's going to be less polarized. Or actually more polarized. This is less polarized. Yeah. And so the inductive effect is, we expect if you expect hydrogen versus oxygen, oxygen should win. Oxygen versus chlorine, oxygen should win, but chlorine's going to put a stronger fight than bromine. Bromine puts a weaker fight. And so even though these arrows are drawn the wrong way here, what it's indicating is that chlorine is going to have a more powerful effect on oxygen than bromine. And what that does is it makes things more or less electron rich. And so these are both oxygens, and both oxygens should have the same richness, but they don't. It turns out that this oxygen in HOBr is more rich than this oxygen in HOCl, and that's because of chlorine. Chlorine withdrawing or sucking electron density away. And so this is called the inductive effect. The inductive effect is this electron withdrawing effect due to what's attached to a particular atom. And so that's going to make this oxygen more electronegative. And what it's going to do is it's going to make this bond more polar, even though it's an HO bond, than this bond here. This bond will be less polar. And so in terms of bond polarity, HOCl is stronger acid. In terms of base strength, okay, so if we plug off the proton, then we're left with this base, which is hypochlorite ion, versus this base, which is hypobromite. So this is more polar, therefore this should be stronger. Acid. Over here, which base is stronger, which base is weaker, and why? So if we just look at the oxygen, they're the same, aren't they? However, when we look at what's bonded to it, then it changes things a little bit. And over here, the chlorine, even though oxygen versus chlorine should win, but this is negative oxygen. And so what we're going to have an inductive effect here versus bromine, which is going to have a weaker inductive effect. And so what that's going to do is chlorine is going to suck the electron cloud away from oxygen versus this. So which base is stronger? This is the stronger base, therefore HOCl is a stronger acid. Or is that right? No, that's not right. Yeah. This is the stronger base, therefore HOCl should be the weaker acid. Because that's less stable. This is the weaker base, more stable, therefore HOBr should be the stronger acid. So now we have a conflict. You see we have a conflict?
Why is OBR more stable? Because isn't OCl, it's like smaller, so it should be more.
Well, that's for hydration. In terms of base strength is its ability to pluck a hydrogen off. So the more negative it is, the stronger the base. The base strength. Then we look at hydration. OCl minus is smaller. Versus OBr minus. And the smaller the size, the more stable the solvated or hydrated ions. This is smaller, therefore more stable. Hydration sphere. So if that's more stable, then that tells us HOCl. So based on bond polarity, HOCl. Based on hydration, HOCl. Based on base strength, HOBr. So we have conflicting data. So what is it? Well, we take a look and measure it. And so the acid strength has been measured. And the bigger the Ka, the stronger the acid. So this is 10 to the minus 8, that's 10 to the minus 9. So it's about 10 times stronger. HOCl stronger. And so it's got to be due to polarity and maybe hydration, because base strength is not. You predict. K is acid strength. It's directly proportional to acid strength. Ka is how much it ionizes. But it's a ratio of the ionization products versus the unionized. The bigger, if it ionized 100%, Ka should be infinite. And so nothing ionizes 100%. But, you know, when you're at 10 to the 6th, that's pretty big, so I'm going to ignore the tiny fraction of unionized. Ka is talked about in Chem 1b. Which one's the stronger acid? H2SO4 or H2SO3? Sulfuric versus sulfurous. Sulfuric is 100,000 times stronger. This goes by powers of 10. With 5 orders of magnitude, 100,000 times stronger. Okay, so tell me why. So we're going to do this. It's ad hoc. We're going to look at the factors that influence acid strength and then see which ones are important here. And hopefully the more we see, the better we'll be able to grasp, you know, if there's a conflict, which should be more important in a conflict. So go ahead and give that one some thought. HO bond. Bond energies, roughly the same. So I'll get back then. If we look at it, it's an HO, the polarities should be the same, but we don't stop there. We look at what the oxygen is bonded to. So in this case, it's an HOS. This is an HOS. So the polarity looks to be the same, but it's not, because this is a sulfur with a +2 formal charge. This is a sulfur with a +1. Which one is going to have a higher electronegativity? A +2 sulfur or a +1 sulfur? +2. And so this bond is more polar. This bond is less polar because the oxygen is going to pull more here because it's being it's having its electron density being sucked away by this sulfur compared to this one here more significantly. So in terms of polarity, then H2SO4 should be the stronger of the two. What about in terms of bond base strength? So let's compare the two bases, the conjugate bases, that form after deprotonation. So if we deprotonate H2SO4 just once, let's say, I'll take off the left proton there. Versus the sulfuric acid here. We want negative charge. The more negative charge, the more basic. When we look at this, we look at the oxygens. Although this has a total of 3, this only has a total of 2. Let's look at one individually. What's the average charge on each oxygen here, these 3? The average charge would be -1. What's the average charge over here? -1. They're both the same charge. But do they have the same charge density? So if we look at this one, is this oxygen more basic or less basic than this one? And so what we do next is we look at the inductive effect here. The inductive effect, this sulfur is +2 formal charge. This sulfur is +1 formal charge. 2 electrons missing here. So even though oxygen versus sulfur, oxygen should win, but this is an oxygen competing with a +2 sulfur. This is oxygen competing with a +1 sulfur. And so +2 sulfur is going to suck the electron cloud more than the +1 sulfur. You see that? And so even though all these have a -1 on the oxygen, this negative is smaller than this negative. And so this is going to be slightly less, this would be a bit more. And so in terms of base strength, there's going to be less negative charge on the oxygen over here versus over here due to the inductive effect. And so this should be a weaker base. Weaker base is more stable. And therefore, H2SO4 should be a stronger acid. So based on base strength, we predict H2SO4. This will be a stronger base. And this has to do with charge delocalization / localization. The charges are localized on these oxygens, but it can be delocalized slightly due to the inductive effect. Inductive effect sucking some of the charge density off there. So if this is the weaker base, it's more stable. Product more stable, H2SO4 should be a stronger acid. And finally, hydration. Which one should be smaller? This one should be smaller, and therefore more stable in a hydration sphere. Although it's complicated because this one has 3 negative, this only has 2. But just based solely on size, this one. If that's the case, then H2SO4 should be weaker, actually. Because this is more stable. This is more stable. That means H2SO3 is more favorable.
So it should be a stronger acid.
It should be a stronger acid. So the last one, hydration, should pinpoint this. The first 2 that we talked about there, aside from bond energies, would be this one. And which one's stronger? This one. And so it looks like polarity is the most significant factor here. Yeah, if the acid is less stable, it's going to be stronger. This is adhering to the octet rule. What we're going to do is we're going to try this with expanded octets. There are 2 primary reasons for expanding an octet. One is to add more bonds. The other is to lower or decrease the formal charge. at this first structure here. The advantage of this is we don't have to expand the octet. Expanding the octet is going to cost energy utilizing d orbitals. If we want to expand the octet, let's just try expanding it by adding one double bond here. If we add one double bond, the advantage is we lower the formal charge on sulfur to +1. The disadvantage is we have to make a pi bond. And what's the hybridization on sulfur? It's sp3 hybridized. If it's sp3 hybridized, there are no unhybridized p orbitals left over. All p orbitals have been hybridized. And therefore, if we need to make a double bond, it can't be with a p orbital on sulfur. For oxygen, we can use a p orbital. But the disadvantage of this is we have to use a d orbital on sulfur. And so we have to form a pd pi bond. A pd pi bond, well, that's okay. I suppose here's a p orbital, and then we'll have a d orbital here. That'll be a d. So we could have a pd pi bond here. And we'll form one pd pi bond here. And then how many resonance forms can we draw for this? How many more resonance forms? Just one. And where would the double bond be? On the bottom. So maybe it's okay. We can decrease the formal charge and we form one pd pi bond. But most of the Lewis structures for sulfuric acid are not going to show one double bond. Most of the Lewis structures for sulfuric acid show how many double bonds on sulfur. They show two double bonds. Why two double bonds? The reason for two double bonds is what is the formal charge now? 0. And so that's quite advantageous to have 0 formal charge. However, the disadvantage of this is we need to form, two pd pi bonds at what angle? What's the tetrahedral bond angle? 109. But the d orbitals are oriented at 109 angles? No, the d orbitals are oriented at 90-degree angles. If they're oriented at 90-degree angles, would this be a good p-d pi bond? Let's say the p orbital were oriented like this on oxygen. And let's say the d orbital were tweaked out a little bit. Is this a good pd pi bond? No, because we're getting poor, we got great overlap here, but we're getting poor overlap here. And so having the angles, we don't have d orbitals oriented at 109-degree angles, so the orientation, the geometry of this is off. So having two pd pi bonds, even though it's great because there's no formal charge, is difficult because we got to form two pd pi bonds at 109-degree angles. That's not going to be easy to draw when the d orbitals are oriented at 90-degree angles. And so, which structure is it? Do we just maintain the octet and have high charge, or do we do some PD pi bonding here? And so the book didn't really get into it, for PD pi bonds, not much. But one thing we could do to keep ourselves safe is this. We can draw all the Lewis structures for this with all the reasonable variations and say that the actual structure is going to be a hybrid of these. And so this would be kind of ad hoc as well, because what we want to do is we want to figure out what is the charge on sulfur. The higher the charge, maybe that's it. Maybe the higher the charge, we have a greater ionic character of the bond. The bonding here is much more ionic in character. Over here, the bonding is more covalent in character. But it's going to cost us. So what I want to do is, let's take a look at the typical. The typical, it used to be a simple rule. The simple rule is if you can expand the octet to reduce the formal charge, go ahead and expand the octet. And so most people, when they look at sulfuric acid, they'll look at this last structure here. And most people, when they look at sulfurous is maybe not as bad because we only have to form one PD pi bond here to reduce the formal charge to 0. Now, if the formal charge gets reduced to 0, which one's the most polar? Let's say bond energy is about the same. Which one's most polar? Earlier, we compared a +2 formal charge to +1 formal charge. +2 is greater. Here, what are the formal charges? They're both 0. So does that mean the polarity is the same? No. It's because formal charge is making an assumption that the bonds are 100% covalent versus oxidation state. Oxidation state assumes the bonds are 100% ionic. So even though the formal charge is both 0, we're going to go to the next backup plan. The next backup plan is what is the oxidation state of this sulfur versus what is the oxidation state on this sulfur. And compare those. And so we know the formal charge is 0. That's not going to help us. But what is the oxidation state? +4. Over here, the formal charge is 0, so that's not going to help us. But what is the oxidation state here? +6. And so which one should be more polar? Which one's going to have a larger inductive effect? +6. +6 is going to pull the electron cloud more, making this a greater delta plus. +4 is going to pull the electron cloud less, making a smaller delta plus. All right, so this is using oxidation state. Lastly, we can look at it based on the number of terminal oxygens. And so another way of doing the inductive effect, which is very common, is having these terminal oxygens suck away electron cloud density. So in sulfuric acid, we have one terminal oxygen sucking electron cloud In turn, it's going to set off a chain. Here, leading to positive charge there. Versus sulfuric acid, which is going to have two terminal oxygens. The two terminal oxygens sucking electron cloud and resulting in more polarized HO bonds, giving us a bigger delta plus. Okay. So based on polarity, we predict sulfuric acid should be. Also based on base strength, sulfuric acid should be. Okay, now what we're going to do is we're going to compare the base strengths using the expanded octet. Next. Which one is going to have more concentrated negative charge? This one or this one? Number one, we have the inductive effect. The inductive effect is this sulfur has an oxidation state of what? +6. Versus this sulfur, which has a +4. And so +6 is going to withdraw more of the negative charge off that oxygen, making this a weaker base. This should be stronger. Based on the inductive effect, this is going to have a larger inductive effect here. This is going to have a smaller inductive effect here. We can also do the same thing with the terminal oxygens. Having two terminal oxygens will suck the electron cloud away from this oxygen, making it less intense, less basic. This one, again, it just has one terminal oxygen. So the magnitude of negative charge is less over here than it is over here. So we got greater magnitude of negative charge. But the inductive effect is usually minor compared to resonance delocalization. So yeah, that's going to drop a little bit. So this is the inductive effect here. But resonance delocalization is much more significant. And what I mean by that is, if we have the fully expanded versions here, how many resonance forms can I draw for this? How many? 3. The 3 would be double bond up and left, and the final one would be double bond left and down. I better draw those, I guess. All right, what is the average charge on oxygen? So we see the negative charge distributed over 3 oxygens. So -1 over 3 oxygens give us the average charge of -1/3 on each oxygen. So that drops the charge down significantly from -1. Versus this. How many resonance forms can I draw for this? 2. So -1 charge distributed over how many atoms? 2. Gives us -1/2. Which one's more basic? -1/2 or -1/3? -1/2. So this is the stronger base. So typically in organic chemistry, you do it. The more resonance forms you could draw, the more stable it is. So this is a more stable base. This is a less stable base. How about for hydration? Well, it looks like sulfurics is smaller. But we know that sulfuric is the stronger acid of the two. And so how you want to approach that, expanding the octet or not. Maybe easiest not to expand the octet. And the data seems to show that when we expand the octet to add more bonds, that is hybridize, like sp3d or sp3d2, calculations are showing minimal D contribution. All right, try acetic acid and methanol. You could work together for this one, but try to figure it out.